Okay, so now let's look at another problem, and this one is basically a cylinder, and it also has a constant magnetization, and we would like to find the magnetic flux, and we're going to take a symmetry point. So we're going to take a point right along the z-axis like this. We have uniform capital M. The size of the cylinder is a radius of b and a length of 2L, and so the origin is in the center here. To find the solution, we're going to need to find the bound currents. Let's start with the bulk value. So we have M constant, so if we take the curl of a constant, we get 0. The bound current inside the material is 0. And of course I mean density, current density. Let's find the surface current density. To do that, we look at the sides of the cylinder, take M cross n hat. For our purposes, on the sides, n hat is equal to the unit vector s if we take s to be the radial component. Just to make this clear, up here on these surfaces, k sub b is equal to 0. And the reason for that is that the n vector is in the z direction, the normal vector. The m vector is in the z direction, so when we take the cross product, we get 0. And the same is true down here, even though the surface normal points in this direction, we still get 0. So all we have to worry about are the sides, and so let's go back and take the cross product. We put in s hat for n hat, here's m, and here's s hat. Talking about m0 times the cross product of these two unit vectors. If you apply the right-hand rule, you will end up with this cross product equaling the phi hat component. So this surface current is flowing on the surface of the cylinder. It's in the phi direction, and so if you take the right-hand rule for the direction of z, phi will be in this direction here as I've shown it. We'll talk then about how to use this k sub b to start calculating the B fields. The magnet is like a solenoid. If you take this surface current density, which we just showed is equal to m0 phi hat. If you take a distance parallel to z on the surface of the cylinder of a length dz prime, then at z equals z prime, the current through this line is kb dz prime. Let's go back to the picture. So here we are with a surface current, and it's uniform all over the whole surface. For a particular z prime, this strip here has a width dz. And so the bound current flowing in this little section here will be kb times dz. So when we look at the cylinder here, we have current flowing on the surface as if it were a solenoid. So consider this little element here that's dz high, and we'll position that at z prime. So the center of this band here is at z prime. If we want the current, the equivalent current through this strip here, we take this dz prime, we take the current density, and we multiply those two together, which gives us then the equivalent di, and that's a bound current. Well, we found the magnitude and direction of k sub b. If we just take the magnitude, the di is equal to this quantity here. If we take the expression for the B field due to a loop of current, if you remember we derived that, it will be related to the radius of the ring, and if you're doing this on a point on the z-axis, it'll be the distance from the center of the ring to the point that you want. The distance from this particular loop to the point z is z minus z prime, and we can see this up here. So we're a distance z prime up here, and then this is the distance that we want. And so you just take z, which is from the origin, and subtract off the z prime. Then you put that into the loop equation, and what you want is, of course, it's going to be proportionate to di. Well, here's di, m times dz, because k sub b is equal to m0, and then the direction is phi prime. So this expression here is just the B field due to that ring. In order to find the total B at that point z along the axis, we just integrate. We're going to integrate over the coordinate z prime, and we're going to go from minus L to plus L. So up here we're going from minus L, which is right here, up to plus L, which is right here. So that will add up all these rings and give us the B field due to all those rings. Here's the integral right here, and if we put that into Mathematica or do it by hand, this is the result of finding the B field at a point Z. If you wanted to, you could change this to a plus and these pluses to make it look a little better. But the important thing is that we have a Z dependence, and of course we expect this to be dependent on the magnetization. The bigger this is, the bigger B will be. And it'll have the dimensions in the equation too, so the radius and the length. Now we did nothing here that prevents us from using this same equation inside and out. This holds for both inside and outside the magnetic material. If we look at the same equation here, this is the result. We can imagine what this might look like in terms of the magnitude of B sub Z along the axis of the cylinder. The first thing to notice, this is a plot where I've just put in some usual constants, so L is 5 times longer than the radius here. So what I've done is shown you here that for a small distance around the origin, this is fairly constant. But as you approach the end of the cylinder, this is falling even inside. This line here and this line here represent the ends of the cylinder. And approximately, and maybe exactly, I didn't try to figure it out, you're at about half the maximum B inside the material. If you see how it falls off as a function of Z, yeah, by the way, just don't forget, this is the Z axis. This is going up, this is going down. And so what you see here is that it falls off fairly quickly outside. If you were to use this for any practical purpose, it's really only close to the ends of the cylinder that you'd have a B that is non-significant. If we let this thing get longer and longer, so I let the L go to infinity, then what happens is this basically gets flatter and flatter, so this would be for another value of L much larger. And if you go to infinity, this basically is a straight line at the magnitude 2. So the magnitude right in the center doesn't change at all, but as you make the cylinder longer and longer, you start getting a very uniform field, and that will be inside. It's inside the material. So again, if you want to use the magnet, and you want it to have a field that is basically near constant inside and it might actually extend further, the longer the magnet that will occur. Prove me wrong, take this and plot it for different values of L, and you'll be able to see what that field looks like. The way we've done this problem, this will hold up for both inside and outside of the magnetic material. So we get the whole answer immediately. Well, let's look at another example, and this is another one of these solenoid problems. So we've got the typical solenoid with N turns per unit length. The current through the windings is I coil, and we're going to stick into the solenoid a concentric cylindrical magnetic rod which will have a radius that's smaller than the radius of the solenoid. So what that means is that inside the center region we're going to have an air gap and the magnetic material. And so our goal is to find the vectors H, B, and M in both the air gap and inside the magnetic rod. And some additional problems are to find the ratio of B in the rod to B in the air, so inside the solenoid. And the surface current density on the surface of the rod and the bulk current density within the rod. And these are the bound currents. There are no free currents inside the material. They're all in the solenoid coil. So here's what it looks like. You have the solenoid out here at radius B, and you have the radius of the magnetic rod A, and these are concentric, so the symmetry axis is right down the middle of both of these cylinders. The current direction is as shown, so this is coming towards us, and this is going into the plane of the picture here. So here we have the mu of the rod, which is greater than the mu of the space in between. Here's air in between. To start the solution, let's consider two loops. Amperian loops, which are going to be both inside and outside. The first loop will be the loop that has a portion in the air outside of the solenoid, and then back coming through the magnetic material and closing. The other loop will be back into the air gap over to this part here, and then down back through the whole thing into the region again outside of the solenoid. We differentiate these with the primes. This is 2' to 3', this one's 2 to 3. We're going to consider Ampere's law for H, and if you remember, it's the integral of H around a closed path, which is equal to the free current that's enclosed by that loop. If we take this loop here, let's just call that C, we would first realize that we have H not depending on the presence of magnetic material. It only depends on the free currents, and that's being forced upon us by this equation here. Where are the free currents? Well, it's the currents flowing through the coils. Even if there are bound currents, they do not contribute to H. For a long solenoid, just like the B field, we can consider that H anywhere inside is constant. So we would have H fields running through both the region out here and in the rod, and they would be equal. So that's because this is an infinite solenoid if we wish. If we go outside of this solenoid, just like in the case of the B field, H outside is equal to 0. And the reason for that is because there's no total free current that's enclosed by the loop that would actually go all the way outside like this. So you'd be canceling the currents enclosed by the loop, and so therefore you get 0 for the field. So we want to consider two loops. The first loop is the one shown here where let's say we start here, we go around. So this part of the loop is inside the magnetic material, whereas the bigger loop goes back into the air gap. Just keep in track, this is 2 to 3, this is 2' to 3'. This portion here is outside of the solenoid. Along the portions of this loop where we have H perpendicular to dl, we get 0 for the dot product. Realize the parts that we're talking about are the ones along this portion of the loop. So for example, if you consider H in the direction of Z, which is the assumed direction because of the direction of the current, then you're perpendicular to the dl that's along the loop, and so you'll end up with 0 contribution to the H dot dl. If you come out here, H is equal to 0, and so you don't get any contribution to this part of the loop. So finally, you're left with the only contribution is 2' to 3' or 2 to 3. And so we'll talk about that then. Because of the fact that these loops do not depend on anything but the free current, both loops are cutting this part of the solenoid, then we're going to end up with the same H for either in the material or in the gap. If you take the left-hand side, then you would have the H dot dl. H is parallel to dl. H is constant because of the fact that this is an infinite cylinder. So just like we have constant B, we have constant H. This quantity here will just be H times L when we integrate over this part of the path. H anywhere inside the solenoid, either in the material or in the air gap, times the length L is our left-hand side, which we're going to set equal to the right-hand side, which is equal to this quantity here. We'll go back to the solenoid problems we've done before. We have to multiply the current that's in each coil by the number of turns, and that's just going to be the number of turns per unit length times capital L. If we put all that together, then we have H times L equals this quantity that has an L in it. Cancel the L's, and so we have H anywhere inside equaling Ni coil. That points in the Z direction, and so we end up then with anywhere in the coil inside the solenoid, H will be given by this quantity here. So we've determined H both in the air gap and in the rod, and they're equal to each other. Given H, we're going to assume linearity, and so we can find M and B. And so for linear magnetic materials, M is proportional to H, where the chi sub M is the magnetic susceptibility and depends on the material. And the important thing is that these two are proportional to each other. We can solve for M by just multiplying H by this quantity here, and so here's our M. And so we have a condition then that the more current we're running through the coil, the higher the value of M is. Remember, this is a restriction that will hold for materials that when you turn off the current, you end up with zero magnetization. So you're on a portion of the curve where you basically can reproduce the fact that your M is proportional to I and can go back to zero. If we now go inside the material, we have the relationship that B is equal to mu times H, and so we look at what mu is. We put that first in the equation for B, so we have B times H here, and realize that mu is equal to the relative value of mu times mu 0. Remember, mu sub r is equal to 1 plus chi sub m. We can either leave it as is, this equation here, or we can substitute in for the mu, which is mu 0 times 1 plus chi sub m. So it just depends on what you know before you do the problem. Do you know chi sub m or do you know mu sub r? Outside the material, we have mu equal to mu 0, so B is equal to mu 0 times H, and so we end up with this quantity here. So we found B in both regions, in the air gap and inside the magnetic material. The only difference between these two is this factor of 1 plus chi sub m. For ferromagnetic materials, this is huge, and so you get a very large B inside the material. Let's find the ratio of B in the rod to B in the air. So what we're talking about is the ratio B inside the material to B in the air gap. It's just going to be the ratio of mu to mu 0. And so canceling out the common factors, then the ratio of the B fields will just simply depend on the ratio of these mu's. Realize that this ratio here is what we call mu sub r, the relative value. If you then take the susceptibility version of mu sub r, which is 1 plus chi sub m, then what you're getting is both expressions are the relative permeability, which we know is a dimensionless quantity. So that simplifies then the fact that the ratio of inside the material and B in the air gap is given by this quantity here. And don't forget that B outside the solenoid is equal to 0. The last part is to find the surface bound current and the bulk bound current densities. We take our expressions for the surface current density, m cross n hat, and for the bulk bound current density we get the curl of m. So we put in our m, which we've determined to be this, and the unit vector that we're talking about is the r vector that's in the r hat direction, because that's the normal direction. And let me just go back to remind you what surface we're talking about. We're talking about this surface here. So if this is infinite, we don't worry about the ends, so that's why we're taking this direction here. I said r, but we could call it s hat too, because of the cylindrical symmetry. Using the r hat, then just remember that z hat cross r hat is in the phi direction, so we end up with a surface current that's running around the surface of that rod in the center, very similar to what we did for the problems just previous. Now we come to the curl of m, so we put in our m, we take the curl of that, and because all of these are constants, we end up again with the bulk current density, the bound bulk current density equaling to 0. A picture of these currents would look like this. We have this I coil running around in the solenoid, turns. We have a M which points along the z direction is equal to this. We have a surface current that is on the surface of the magnetic material, and it's along the phi hat direction, and so I've shown you the direction of that current. The magnitude and direction of that current is given by the expression that we have here. If we wanted to, we could represent the current in the solenoid as a current density. If you recall, we did this before, that the surface current density of the free current is going to just be related to the current through the turns times the number density times the direction of that K, which is in the phi direction. Down here, given a coil with n turns per unit length, the unit of n is equal to 1 over length. It's the number of turns per unit length. The number of turns is just a number. We can therefore turn the I coil into a free surface current density by just taking K equal to the I coil, in this case times n, which would give us the expression for K. And so that would be I coil n times the phi direction. So next time we're going to look at some more details about B and H. And I've already said that H can be a tricky quantity, so we'll try to discuss that. And then finally we'll look at the boundary conditions for B and H at an interface. And so what I'm talking about there is we have an interface between two different magnetic materials, one of which could be air, but it doesn't have to be. So the question is, what happens to B and H as they cross over? Do they bend, etc.?